I thought we would pause after talking about the first few computational strategies for addition before we get into this next video where we talk about the last ones. Now remember, these computational strategies are designed to start working with larger numbers now. And so remember, we're trying to help our kids learn to count and measure in increasingly faster, more efficient, and more sophisticated ways. And what that means is faster computational strategies, more efficient computational strategies, and more sophisticated computational strategies. So as we begin to move forward from grades kindergarten and first grade up through fifth and sixth grade, the size of the numbers are getting bigger. And so sequential counting on subitizing, those are not strategies that are going to work for larger numbers. Now, one thing I want to mention here at first is this idea of mental math. The idea of mental math is to be given an arithmetic expression and determining if we can figure out what the size of the target set is without doing any calculations. So we don't want to do any calculations, but we want to take advantage of, what it is we know about numbers and their relationship to each other. But all of it really depends on our full understanding and our ability to facilitate place value. So if we mentally are given something like 63, and I'm writing it down, we don't want to have to pick up pencil and paper to find out what the sum is or the total is for 63 objects and 24 objects, because we can do this calculation in our head. For example, the 6, of course, is not 6, it's 60, and the 2, of course, is not 2, it's 20. So we're really looking at 60 plus 20. Remember, consistent with what we coach our kindergarten and first graders to do, which is to look at the larger numbers first, because those are the easier ones to combine. So mentally, they're not writing this down. Mentally, they're doing the calculation of, okay, 60 and 20, that's 80. And then the 3 and the 4, that's 7. And so no, they put the 80 and the 7 together and they get 87. So they can do that calculation without using pencil and paper. Obviously, when the numbers get larger, it might be a little bit more troublesome because they're trying to keep track of a few more numbers, a few more place values. But mental math is really designed to work with single digit, double digit, maybe some 3-digit numbers, but not much. We'll try one. If we've got 327, 456, let's say, and we're trying to add those together, can we do that in our heads? Can we keep track of the fact that the 300 and 400 is 700, so I've got 700 filed away in my head, and then I've got 50 and 20, which is 70, and I've got 70 filed away in my head, and I've got 7 and 6, which is 13, filed away in my head, and so I know I've got 770, and I've got 13 more to go. That's 770, one more 10 is 80, so it's 783. Now again, we're not asking kids to do that, but we're wanting them to have enough number sense, enough number fluency, and enough understanding about place value that they can do a lot of arithmetic in their head without pencil and paper. And if they can, that demonstrates or illustrates the kids have a very good court presence when it comes to number sense or number fluency, but most importantly, place value, because place value is what makes mental math work. In fact, place value is what makes all of these computational strategies work, especially the ones that are designed to handle larger numbers. In the absence of place value, in the absence of friendly numbers, in the absence of power 10 arithmetic, in the absence of single-digit arithmetic, we can't do any of these computations for larger numbers. So let's go back and see what the next one is that we want to tackle in our list. And so that brings us to what's called value expanded form and place value expanded form. So let's look at those two strategies. And these are sort of leading up to what we might think of is some of the better computational strategies for addition. So let's go back to our smartboard screen. So let's talk about value expanded form. And we actually talked about this earlier when I illustrated how we're going to take advantage of friendly numbers, power 10 arithmetic, and single digit arithmetic. So I'm going to pick out two new 3-digit numbers to add together. And so let me make up 472 and add it to, let's see, 849. And I want to know if I were to take those two groups of objects, say it's 472 ping pong balls in one box and 849 ping pong balls in another box, if I were to dump those ping pong balls out of those two boxes and put them all together in a single box, how many ping pong balls do I have in that single box? That single box, of course, being the target set. How big is it? Well, this is not a compatible pair. It's not a compatible pair for me, probably not a compatible pair for you. So the idea is, how do we manipulate this? How do we modify this arithmetic expression into one where we were taking advantage of power 10 arithmetic, friendly numbers, single-digit arithmetic, or combinations thereof. And value expanded form, recall from earlier sessions or from our classroom work, that what we do is we decompose these numbers into their place value expressions. And that's what the 4 means. It means 400. 7 doesn't mean 7. It means 7 tens, or 70. And 2 being in the ones position means 2. And then moving over to the second box of ping pong balls, I'm going to split it up into 3 boxes. One with 800 ping pong balls, another one with 40 ping pong balls, and a third one with just 9 ping pong balls. Once again, why would I do that? Well, I don't have to work with 472 ping pong balls all at one time and 849 ping pong balls all at one time. All I have to do is split the first box up into three boxes of ping pong balls. One has 400, one has 70, one has 2. And in the second one, I split that group of, or box of ping pong balls up into a box of 800, a box of 40, and a box of 9. Why would I do that? Well, these numbers are easy to work with. These are all friendly numbers, and power 10 arithmetic, which is what our kids are learning in the second grade, they know that 400 ping pong balls and 800 ping pong balls is 12 100 ping pong balls, or that's 1,200. Then they know that 70 ping pong balls and 40 ping pong balls, or 7 tens and 4 tens, is 11 tens. And finally, they know that 2 ping pong balls and 9 ping pong balls using sharing is 10 plus 1, which is 11. Now they've added the 6 boxes of ping pong balls, which is essentially what we did when we wrote down the value expanded form. I changed one box of 472 to a box of 400, a box of 70, to a box of 2, and the 849 ping pong balls into a box of 800, a box of 40, a box of 9, and I've already told you why we would do that. I can do the calculations on these. Now it's just a matter of rewriting it, and I'm going to put this 1,000 of the 1,200 over into the thousands column. I'm going to leave 200 behind because it's 2 100s. And the 110, I'm going to leave 10 here, but I'm going to push 100 down into the hundreds column. And the 11, I'm going to leave 1 here and push 10 down into this column. Then I'll add those together to get 1,000, group of 1,000, a group of 300, a group of 20, and a group of 1. And in standard form, that will be 1,321. 1,321. And this strategy is called value expanded form. Now, value expanded form is actually going to be the one that will get us to one of our next computational strategies, which is called table array. But before I look at table array, I want to go back and look at what's called place value expanded form. So I'm looking at place value expanded form. And this time, we're focusing not on the value of the digit, but the position that it's in, what its place value. Let me go back to the previous page. Here, the value expanded form was to look at each digit and split this number up into 3 groups, group of 400, a group of 70, group of 2. And so we've written down the value of each of these digits. In place value, we simply write down the the place value and count that. So let me go back and see if I can remember these numbers. This is 472 and 849. And I want to know, once again, if I have two boxes of ping pong balls, one with 472 in it, one with 849 in it, if I merge them together to form a single set called the target set, how big is it? This time I'm going to rewrite them not in their value expanded form, but in their place value expanded form. And this really sets the stage. We're not saying that this is a good or a best computational strategy, but we want it to be one that the kids understand, because they're going to start using these ideas in the 5th and 6th grade. So we're helping them get ready for the 5th and 6th grade. So instead of writing the value of 4, I'm going to write down what it means. It means 4 times 100. The 7 means 7 times 10. And the 2 means 2 times 1. And the 849 means 8 times 100. And the 4 means 4 times 10 because it's in the tens column. The 8's in the hundreds column. And then finally, the 9 is in the ones column, so it means 9 times 1. And I'm going to add, not in value expanded form, but in place value expanded form. And again, we start not at the right-hand end, but we start at the left-hand end. Because why? That's what our kindergarten and first grade teachers are coaching our kids to do, and we don't want to change the plan for them. So we're starting at the left-hand end. So this means 4 100s and 8 100s is 12 100s. And 7 10s and 4 10s is the 11 10s. And finally, 9 1s and 2 1s is 11 1s. And I've written everything in place value expanded form. So this is place value form. And so now I want to write this as 1200 plus 11 tens is 110 plus 11 ones is 11. Whatever that number is, 11. And then I have to put it back in standard form. When we did this in the problem before, so again, we do the very same thing. I can even leave the 1200 together and pull 100 over here and write this as 13 100s and leave the 10 there. Pull the 10 from 11, write another 10 there, leave the 1 by itself. And remember this, how the kids write this down is up to them. Remember, kids think and learn differently. So the way that they would rearrange or write these numbers so they can get them into a form where they can write down the standard form for this number, how they do that is not important, just as long as they know that they're grouping things to get them together so they can write down the standard form. So right now this is 1300 plus 20 plus 1. So it's 1,321. So here's the number in standard form. And that's an illustration of place value expanded form, where we're using the place value representation for these two numbers, 472, 849, instead of the value expanded form. Now, as I said before, the value expanded form is what leads us to what's called table array computational strategy. And so let's see how that plays out. I'm going to do it with the very same numbers, 472 and 849. And what I want to use is what's called table array. So this time we're going to write the numbers vertically, and I'm going to write them in what's a classical way to write these numbers down: 472, 849, and I want to add them together. Now, at the beginning, we want the kids to understand exactly what it is that they're doing, so we're going to write in a few more details, and we would like the kids to go ahead and follow through with these details. So again, as before, we're not adding right to left, we're adding left to right, because why? That's what they're taught, or that's what they're coached to do in kindergarten and first grade. So in this first problem, I'm actually going to out to the right-hand side, I'm going to ask you to ask your students to write down so they understand what it is that they're doing. So instead of writing it in value expanded form, they're just going to skip that step and simply note out here to the right, they're adding 800 to 400. That's reinforcing the idea that they understand what it is that they're combining here when they're combining the two boxes of ping pong balls. So they know they're going to add a group of 400 to a group of 800 and get 1200. Then they're going to move over to the next column and write down exactly what they did. They added 70 to 40, and they know that that's 7 tens and 4 tens, which is 110. Or they might take 30 off the 40, write it with the 70, because that's a combination. That makes 100, and there's 10 left behind, so that's 110. And they're going to line those numbers up correctly, putting the 1 in the hundreds column, just as they did with the 2 in the hundreds column. And then finally, they're going to take the 9 plus 2. And notice I'm writing those out to the side, but your kids are eventually going to skip that step. But let them figure out when they are comfortable in doing that. Let them decide to ignore this idea of writing these down separately out to the right. But it's reminding them exactly what they're doing when they're combining two boxes of ping pong balls and they're choosing to add the numbers in a way they want to add them. The friendly numbers, 400, 800, the friendly numbers, 70, 40, and finally the two single-digit numbers, 9 and 2. So finally, 9 and 2 is 11. I'm adding left to right, so there's 1, 1,000, adding the thousands column. In the hundreds column, there were 3 100s. In the tens column, there's 1 and 1 or 2 tens, and finally in the ones column, there's only 1. So they already have the standard form. There it is. 321 ping pong balls when we merge the two boxes of ping pong balls together. And that's called table array. And you can do it with larger numbers, or you do it with multiple numbers as well. So instead of adding these numbers together, they might take off with, say, 386, 472, 849. And they would go through the same steps. So they would write out here to the side what it is that they're doing, which is to add the 300 to the 400 to the 800. But you're simply going to say, well, 800, 400 is 1,200, and 3 more is 1,500. And then 80 plus 70 is 150, or it's 15 tens, and 4 more is 19 tens, so it's 190. And finally, the 6 and the 2 is 8, and since they're adding it to 9, they know there's a quick way to add 9 to 8, and that's to push one of the part of the 8 over to the 9 and make it a 10, so it turns out to be 17. And now they're ready to merge these and write the final answer down here. They may have to go down a second level. Let's go back and see what final strategy we have to look at. And so we've talked about value expanded form, place value expanded form. We talked about mental math. We talked about table array. And we're going to talk about lattice array. Let me make this comment one more time. We're not trying to present a whole bunch of strategies, computational strategies to our kids with the idea that they're going to memorize all of them or to learn all of them. We just want to make sure that when we do present these to kids, that if they don't like one particular computational strategy, you've got another one. There's actually a hop, skip, and jump strategy that's not in the list that I forgot to put in the list, quite frankly. But there is a hop, skip, and jump strategy for addition, and we'll talk about that perhaps in the next session. But the last one I want to talk about, which is called lattice array. And once again, we're trying to help our kids see a computational strategy that makes sense to them. One that they're not just memorizing, but they actually understand. So let's look at the lattice array, which is the final computational strategy we'll look for in addition. So let's go back to our smart board. Let's take 643 and let's add it to 879. Let's figure out what the size of the target set is. Now these are two numbers that we haven't worked with except at the very beginning of one of our videos. And I want to use what's called lattice array. And so it looks kind of contrived at the beginning, but you'll see how it plays out. So I'm going to take the 800, I'm going to write these in such a way that they're not right up against each other, and you'll see why in just a moment. I want to add these two groups of objects together, and this time what I want to do is I want to create a box underneath them in a way that looks like this, and I'm going to put a diagonal down each of those boxes, and this is called Lattice Array. And it's just a different way of looking at how to add two or more numbers for that matter. It works just as well if I have two numbers. It works just as well with three numbers or four numbers. But under each column, I'm going to put a little box with a diagonal in it. And here's what we're going to do. It doesn't really make any difference whether we add left to right or right to left, but here's what we're going to do under each column without worrying about this idea called bundling or carrying. Here's what we're going to do. Remember, the 6 and the 8 represent what? 6 100ths and 8 100ths, and so that's 14 100ths. This is in the tens column, so it's 7, and 4 more is 11, so it's 11 tens. And then finally, the 9 and the 3 are 12 ones. And now what I've done with this little artificial diagram is the 2 is in the proper ones column, and these ones are in which column? Remember, this was a 12, and so that's really 110. And remember, this was 11 tens, and so that's 100 and 110. So this is the tens. This column right here, or the better, this diagonal is the hundreds. And finally, this column right here is the thousands column. And all we need to do is put together those numbers. And so this is, all this leads to what? 1,522. So here we go. 1,000 in the thousands column. Add the 4 and the 1, which is in the hundreds column or diagonal. So that's 5 100ths. In this column right here, which is the 10, or in this diagonal is the tens. So there's 1 and 1. That's 2. That's 20. So that's 20. And then finally in the ones is 2. So it's 2. So it's 1,522. That's called lattice array. Let's do one more just for the heck of it. Let's take 748, add it to 367. I want to know how big that set is, the target set, when I merge those two groups of objects together. Once again, I'm going to write it as 748. I'm going to write them a little further apart from each other to allow for those boxes. I want to make sure that the boxes are big enough so that the kids see exactly what's going on. Now remember, last time I added left to right, and I want the kids to practice adding left to right, but you can really add left to right. You can start in the middle and move to the outside. So I'm going to start in the middle column. Remember, this is 4 tens and 6 tens. So that's what? 10 tens, 1 0. The 7 and 3 is 10, but it's 7 100ths and 3 100ths, so that's 10 100ths, so I wrote it down. And then the 8 and 7, that's 15. So write the 15 there. Once again, this first diagonal here is the ones diagonal. The second one is the tens diagonal. The third one is the hundreds diagonal. And the fourth one is the thousands diagonal. So just looking at them, it's what? 1,115. So here's the standard form. And that's what's called lattice array. Again, am I advocating and saying that that's a great computational strategy? No, I'm just saying it's a different computational strategy. And some kids may just, think this is just as good as chocolate ice cream. But they're going to be able to choose, if not this strategy, table array, or the one I haven't mentioned, which is called hop, skip, and jump. And we'll come back to that later. So the next session, we're going to look at the arithmetic principle called multiplication. And And so we'll start on that one in the next presentation.